Howdy folks, this discussion is going to be all about the linear algebra behind dimensionality reduction. As usual, at the GitHub link in the description, you'll be able to access this Jupyter notebook with all the code used in this discussion, as well as a bunch of extra written notes. And before we get started, let me just quickly preface that this discussion is going to be about the general linear algebra behind dimensionality reduction. We're not going to get into any specific techniques or methods of dimensionality reduction. This is just the general linear algebra behind it. So with that said, let's begin. Alright, so dimensionality reduction is exactly what it sounds like. If we have some matrix A, it has dimensions m rows by n columns, and the idea behind dimensionality reduction is we want to reduce the total number of dimensions that we're working with. But really only kind of, because you see there's two flavors, if you will, of dimensionality reduction. The first flavor is that we're just going to remove the information that's contained within the higher dimensions of our matrix that don't really matter that much, but we're still going to keep the same m rows and n columns shape to our matrix. But with the second flavor, we're not just going to reduce the information, we're going to actually remove dimensions that don't really matter that much, which raises the big question when doing dimensionality reduction, which is what dimensions matter and how do we figure out which dimensions matter. And the way that we do all of this is with what's arguably the most useful matrix decomposition, which is the singular value decomposition. If you need a refresher, you can check out the discussion I did previously, linked in the description. When we do a singular value decomposition, remember that we're getting left and right singular vectors paired with a singular value to form what I like to call is a singular trio. Multiplying the left and right singular vector forms a rank 1 matrix that is scaled entirely by the singular value. And what do we know about singular values? Well, they're all strictly positive, and with our sigma matrix, they're sorted from greatest to least. That means that there are going to be some singular values or some rank 1 matrices that are scaled very minimally. Think about some very, very small floating point number. Some tiny little epsilon on order of, let's say, like 10 to the minus 3 or 10 to the minus 6, whatever you would consider to be small in the case that you're working with. That would mean that when you're reconstructing the A matrix as a combination of the different rank 1 matrices, the first k, k just being some integer value here, the first k rank 1 matrices are going to have significantly much more impact in reconstructing that initial A matrix. And so if we establish a cutoff point and we don't use the information contained with those rank 1 matrices that are scaled by really, really, really small singular values, we're throwing out the information contained within those rank 1 matrices, or really those higher dimensions. And that's what the first flavor of dimensionality reduction is all about. If you saw my discussion on data compression using the SVD, where we took a boat, converted it into a matrix, and then did a singular value decomposition on it, and then reconstructed that boat image with combinations of more and more rank 1 matrices scaled by the singular values, or singular trios as I like to call it, you could see that at a certain point, adding more and more rank 1 matrices really didn't contribute too much to the overall image. At a certain point, we could have just cut it off. Now, that didn't just allow us to compress data. This is also a way for us to remove noise from a system. We didn't actually change the dimensions of our boat image. The boat image was still 512 pixels by 512 pixels. But we removed information from higher dimensions that just didn't really matter, or was more or less just noise at the end of the day. And so this first flavor of dimensionality reduction is very useful in that regard. If you need to keep the dimensions the same, like say you have an image like the boat image, you can still get rid of the information from higher dimensions that are more or less just noise that don't really matter too much to the rest of the overall picture or the rest of the overall matrix. It's a great way of being able to simplify the matrix that you're working with and ensure that you're dealing with almost a clean or less noisy matrix. Okay, but now let's move on to the second flavor of dimensionality where we're not just going to be removing the information contained in less important dimensions, we're going to be removing that information, but we're also going to be actually changing the shape of our A matrix and getting rid of those dimensions. And to explore this second flavor of dimensionality reduction, we are going to take a look at the very popular machine learning dataset called the iris dataset, which consists of petal length and width and sepal length and width measurements of 150 different iris flowers of 3 different classes: setosa, versicolor, and virginica.
And these are iris flowers. You got the petal, and I think this thing on the inside is the sepal. I'm not sure. I should know this because I do garden, but here's these are some purple iris flowers.
And we can visualize these different measurements right here, and you can see that of these different measurements, we have things kind of all over the place, but the main goal of this data set is that we want to do some bit of machine learning to differentiate between these 3 different types of iris flowers. And you can see that with these sepal measurements, if we look along the diagonal here, they're all kind of bunched up, whereas the petal measurements are a little bit more dispersed from one another. And if you compare petal length versus petal width, sepal length versus sepal width, petal length versus sepal length, whatever, so on and so forth, you can see that some of these different subspaces between the 2 different features actually look like it would be a little bit easier or a little bit better for you to write a clustering algorithm or like a classification algorithm or do some bit of machine learning to this data set to differentiate between the different types of iris flowers: setosa, versicolor, and virginica. So what we're going to do, we're going to load in this iris data set. You can see that from the dimensions, it's 150 rows by 4 columns. So it's 150 different iris flowers. We've got the 4 columns: petal length, petal width, sepal width. And we're just going to do a simple singular value decomposition on it. As I said before, we're just looking at the general linear algebra behind dimensionality reduction. You'd get more into the statistics, you'd get more into kind of cleaning up this data set or transforming it a little bit. But when we do the SVD, you can see that we get 4 singular values for 4 dimensions. The first singular value is 95.9599. The second is 17.76. That's very patriotic if you're American. I didn't realize that until now. Not to go off on too much of a tangent, but then the second 2 singular values are very, very small in comparison to the first 2. We've got 3.46 and 1.88. So clearly, the first 2 dimensions matter much more than the second 2. If we were just doing the first flavor of dimensionality reduction, you'd probably reconstruct that matrix with just the first 2 singular trios, or the first 2 rank 1 matrices scaled by the first 2 singular values. But a better way of looking at this is if we use something called the explained variance ratio. Now, I don't want to get too deep into the statistics or anything like that, like I already said, but this is the ratio of how much variance of the total data set is contained within each one of these dimensions. I like to think about it a little bit more in terms of just relevant information. So how much information is contained within each one of these dimensions. That's just what my brain goes to. But remember, this is variance. So in the first dimension right here, 96.53% of all of the variance or all of the information of the original A matrix is contained within just this first dimension. So if you were to just use the first dimension, just use the first singular value multiplied by the rank 1 matrix from the right and left singular vectors of that singular trio, you would have 96.53% of all of the information contained within that data set. But if you actually use the first 2 dimensions, that second dimension has 3.31% of all the variance or all the relevant information contained within that second dimension. So if you combined the 2 of them and just used the first 2 rank 1 matrices scaled by their singular values, you would have 99.84% of the original matrix's information just from those first 2 dimensions. You could use half as many dimensions and still have 99.84% of all the information contained within the original matrix. So why even bother using those last 2 dimensions? So let's just not even use them. We're going to compute a new matrix called Z here, which is just going to be A multiplied by VK, where K is 2 for those first 2 dimensions, and this is going to give us a 150 row by 2 column data set. So once we compute this new Z matrix, that's 150 rows by 2 columns, it's the reduced data here, and we plot this out right here, you can see that we get something that looks remarkably similar to what we had with just the raw data plotted out from before. We have the first dimension running along the x-axis and the second dimension running along the y-axis, and these are just arbitrary dimensions. Again, we don't know what these dimensions are, but with this subspace, you can see that it's going to be really easy for us to differentiate Setosa from versicolor and virginica, and there's not too much of an overlap between versicolor and virginica. So this is going to give us a really nice and easy subspace to work with if we want to start to try to differentiate these three types of iris flowers in this data set, and we're using half as many numbers to do so. Now again, we could just as easily go back to the first flavor of dimensionality reduction, and we could recompute the A matrix as 150 rows by 4 columns. But why do that if we only need 150 rows by 2 columns? But if we do 150 rows by 4 columns, this gives us the opportunity to compute the Frobenius relative error, or really just, it's the difference of two different matrix norms, which if you don't know what a matrix norm is, I realize I haven't done a discussion on those. It's no different than a vector norm, since matrices are just collections of vectors. So all you're going to be doing is taking a matrix norm of our A matrix and then the reconstructed matrix with just the first 2 dimensions involved, and this gives us a Frobenius relative error of 0.0403. So there's a very, very minimal difference in direction in the vectors between the A matrix and that A matrix reconstructed with just the first 2 singular trios, or the first 2 rank 1 matrices included. So to quickly summarize, why would you decide to use dimensionality reduction, or when would you decide to use dimensionality reduction? Well, you'd use it to either compress data, remove noise from a system, simplify your system just generally, or to identify the most important dimensions of your system. And that's what makes dimensionality reduction such a powerful tool. And it's really used in a few different areas of STEM, but it's particularly an important technique in machine learning. And that's probably why most of you are paying attention to this discussion. So let me briefly make a quick connection between what we've discussed here about the linear algebra behind dimensionality reduction and its use in machine learning. We're going to take a look right here. I'll leave this linked in the description. This is a page, a little cheat sheet, if you will, from scikit-learn. Again, a very popular machine learning library. And you can see right in here, one area of this entire flowchart is just dimensionality reduction. So here you've got regression, you've got classification, you've got clustering, whatever. Dimensionality reduction is its own thing. And so if we follow this, let's start from the beginning, and we've got more than 50 samples, great. Are we predicting a category? No. Are we predicting a quantity? No. We're just looking at our data. We're just looking at our data. Then we move into dimensionality reduction. And so this is a way for you to kind of explore a data set, figure out what matters, figure out what doesn't, and you can go on from there. But folks, that's the basic general idea behind dimensionality reduction, or the linear algebra behind dimensionality reduction, I should say. And it's really all just powered with the singular value decomposition. Okay, that said, thank you all very much for watching. If you have any questions, comments, or concerns, don't hesitate to let me know. And if you found this helpful, useful, informative, or even entertaining, interact with it in some way. That way, it will tell the algorithms of the internet that you found it useful, and it'll make it much more likely it'll recommend it to somebody else looking for something similar. Thanks again very much for watching, and I hope to see you all again next time.